In high-stakes cyber-physical environments like surgical robotics and aerospace, functional safety relies almost entirely on probabilistic software. Engineers trust millions of lines of code to govern heavy, high-voltage machinery. This reliance creates two distinct vulnerabilities. First is agentic drift, where an updating AI model unpredictably alters its safety parameters over time. Second are TOCTO, time of check to time of use, exploits, where safety conditions change between the moment the software verifies a command and the millisecond the hardware executes it. System architects typically patch these gaps using real-time operating systems or hypervisors, but these are still software layers. If a threat actor or a software hallucination bypasses the administrative layer, those digital safety limits can be stripped away entirely. Once that digital barrier falls, non-deterministic software code suddenly gains complete, unthrottled control over the physical motor rails. When safety boundaries are written in mutable code, autonomous machines remain unpredictable. The specific nature of software makes it impossible to guarantee a physical result. Securing high-stakes mechatronics requires shifting safety enforcement from software to immutable physical hardware. This operates on the policy as physics inversion triangle. The hierarchy is strict. Artificial intelligence proposes an action. Physical hardware governs the parameters, and humans hold the final decision. The execution substrate for this doctrine is the A13 unified core. It replaces digital firewalls with a locked, deterministic silicon cage. This architecture utilizes a library of modular hardware invariants. These physical constants are designed to scale across different high-risk industries without the risk of software modification. True human sovereignty over critical systems requires a structural shift. Functional safety must be moved out of the realm of software and encoded directly into physical laws. This architecture was originally developed for clinical elder care. The Nightingale Anchor Protocol, or NAP 4.0, was designed to protect the silent elder, patients who cannot communicate their needs or contest algorithmic decisions. This schematic maps out the A13 governance core, replacing probabilistic safety models with a physical bedrock. At its base is P-Life 1.00, a strict binary where harm equals death, hard-coded into read-only memory directly on the silicon. To monitor the patient environment without violating privacy, the protocol utilizes the 3 zeros privacy system. It omits optical cameras and audio microphones in favor of recessed infrared LiDAR. The sensors capture raw distance point cloud data and immediately convert it into an abstract 96-cell voxel grid. A patient's physical presence is tracked purely as anonymous geometric shapes. By erasing identity at the sensor level, patient privacy is enforced by the laws of physics, bypassing the need for mutable software privacy policies. This diagram outlines the A12 sovereign appliance, caging advisory AI via the N layer and D layer. Inside the N layer, the P-register P006 CPU cap is hardwired into logic gates, restricting compute to exactly 1.1 times the baseline. This physical starvation ensures the processor lacks the clock cycles to execute independent predictive pathbinding. Machine-generated trajectory planning becomes mechanically impossible. The N layer also enforces a sacred pause, a mandatory physical delay of up to 1,000 milliseconds. During this window, the system requires validation from a tripartite latch, a biometric scan, a cryptographic USB token, and physical pressure on a foot pedal. If that timing gate is violated, or if an input is missing, the D layer deploys the U7 sovereign brake, severing all power to the motor rails in under 1.05 milliseconds. These physical interlocks act as a fixed mechatronic cage. They quarantine non-deterministic software, ensuring it can offer clinical guidance but possesses zero physical routing traces to initiate mechanical action. Art illustrates the final piece of the architecture, the A7 bridge layer. The A7 acts as the final deterministic translation hub, connecting the isolated core to external cyberspace, aviation, and tactical networks. The defining hardware feature of the A7 bridge is a physical 3.0mm opto-isolated air gap that separates the logical translation circuits from the active motor energy rails. Data does not travel across this barrier via electrical current. Instead, it transmits strictly one way as flashes of light across the physical gap. The return copper receive traces, the wires required to send feedback or receive reverse commands, are physically omitted. Because the physical copper pathways for reverse signaling do not exist, a remote command injection into the motor drive rails is a mechanical impossibility. This hardware-first approach allows these invariants to scale beyond clinical wards, migrating securely into extreme cross-domain environments. Under the UN Space D track, the A11 Jupiter variant deploys this architecture for deep space payload protection, governing robotic arms in low-gravity environments. Operating in a vacuum presents a unique physical challenge. The system must prevent kinetic reaction forces from transferring torque back into the host spacecraft. To solve this, the active movement vector is restricted to the Jacobian's null space. This mechanical projection ensures that dynamic forces zero out before they reach the base joint. The deterministic physics that secure an elder care hospital bed are identical to the physics securing a Mars trajectory payload. The A13 core, the mechatronic cage, and the A7 bridge layer lock into a unified architecture. It is shielded from competitors by paper patents and trade secrets, and protected from AI drift by the strict limits of hardware starvation. The entire system operates on one doctrine. Software provides the observation, and the human holds the decision, but physics enforces the boundary. By embedding functional constraints into the circuitry, the system forces humans out of the autopilot trap, addressing the crisis of automation bias at the substrate level. Functional safety for autonomous mechatronics is defined by the physical silicon gates. By moving the safety envelope into the hardware, the system's limits are enforced by physical law.